Okay, let's get going. We had so many delays. Now, a quick review of what of the Sunday's recording. We were going over serviceability, so we noted that this is one of the three S's of design, with safety for safety, strength, serviceability, and stability. So there are various aspects of serviceability. Some of them we do learn in the undergraduate course, but we will go a bit beyond that. The first one is this is just review. Okay, it's limiting excessive deflections, cracking, vibration, and so on. So the two main aspects are crack widths and deflections. So if you remember, we said deflections happen due to mainly four reasons: the temperature, shrinkage, immediate elastic deformations, and creep, right? So then we briefly went over ASD versus LRFD. This you all know, you can even listen to the recording. In the allowable stress, you keep everything in the linear elastic range, and so you don't need to worry too much about serviceability. However, when we come to LRFD, we are using the actual ultimate strengths of the material. So we do need to especially consider serviceability. We said there are two ways of considering serviceability in LRFD. So one is, I go back here. We will keep the ACI 318 open. Okay, let's wait for that to pull up. So basically, there are two ways of taking care of deflections in LRFT. One is you follow the code specifications for the minimum member thickness. Then if you provide the minimum member thickness, we don't need to especially calculate deflections. But if we are not, a lot of times we are limited by various constraints, architectural constraints, or available space. So we might need to provide thinner members than what the minimum ACI 318 recommends. So in that case, we will specifically need to check deflections. Okay. Now about cracking, we went over very briefly. So the main points are two. One is the spacing between the rebars, and the other is the cover, the clear cover. So if you put very few rebars, large rebars spaced widely, then you will have very few cracks, but they will all be big. So that's not what we want. If you have bars of smaller diameter but spaced quite closely, then we will have many hairline cracks throughout the beam, right? By the way, we only need to worry about deflections for beams, and since columns, it is not, I mean, even for cracking, we need to worry about beams. Columns are under compression most of the time, and we don't, unless it is under flexure, we don't need to worry about cracking. Now, and like we said, the cracking is a must for regular reinforced concrete beams, because without the cracking, the steel does not even start to carry any substantial stress, right? All this, you have the review, you have this recording as well, and from your undergraduate. If your steel has not, if your tension phase has not cracked, that is, you have not reached the cracking moment, your steel is not taking any significant, it's not contributing in any significant way. Okay. Now, we said mainly the information in the code is coming from two sets of research. One is by Gergely and Lutz, and one is by Frosch. So let's get the 318 open there. Okay. Need to wait for that. Okay. So both of them, they account for your bar spacing versus clear cover. So this is the equation of Gergely Lutz. It looks like that. And the equation of Frosch is like that. Basically, what they are saying is if you have a certain clear cover, let's say let's look at, for example, Frosch equation, the purple curve. If I have a clear cover of 2 inches, suppose, then I cannot have a bar spacing of more than 8 inches. So if I have that, my crack widths will become unacceptable. Okay, that's how you read these two curves. Now, in your code, what is followed is your code specification is a compromise between Gergely, Lutz, and Frosch. That's the straight line that's much easier to implement. And this basically tells you that depending on your clear cover, you need to have a certain maximum spacing. You cannot go above that. This is your maximum spacing required. Okay. The main parameters here, they are the stress at service loads in the tension steel, that's Fs. And beta is the ratio of H2 to H1, what you see here. H2 is the distance from tension phase to the neutral axis. H1 is the distance from the centroid of the rebars to the neutral axis. Okay, so now based on that, you could, your DC is the distance to the rebar centroids from the tension phase. That's DC. And area, A is the area surrounding one rebar. Okay, you can calculate it based on the rebar spacing and like that. Okay. 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 Now we just solved a problem where we check whether the spacing is adequate according to the code requirements. Let me see if I'm able to open up the code. Okay, so I think not able to search, that's the problem. Okay, there's our ACI code. Okay, while that sets up, okay, here I can show you quickly. Let's say that you're looking at beams, right? So for beams, there is this go to design limits, and you can see that there is a minimum thickness of the minimum depth of the beam that you need to provide. based on the end support conditions. Okay, so if you don't provide this much, you definitely have to show deflection calculations in your design. Okay, similarly, you can see the requirement for one-way slabs, and all of your general serviceability requirements for deflections, crack widths, and so on, they are all in chapter 24. Okay, so we keep going. In this particular problem, if you do the calculation, then you will see that your S max comes to 10.44 inch based on your code, and your spacing that you provided between your rebars is 5 point something, so that is within your maximum, so that's good. Now let's come to the topic of deflections. Like I said, this is the way we calculate the deflections is dependent on the loading history of the structure. Now, in the Sunday's recording, I spent a bit of time on this. So can any of you tell me, did any of you get a chance to go over that part where we are discussing how to calculate the deflection based on the load history? Sorry, I was muted. I don't know if any of you said something. Okay, that's fine. I hope you did get it. So there are basically we have two deflections. One is immediate or elastic deflections, and the other is the long-term deflection or creep. So we said from your basic mechanics of materials, you can obtain a formula for deflection. So that is usually of the form. For example, for simply supported case, you have your midspan, deflection at midspan to be 5 over 384 WL power 4 over EI, right? So you usually have it in the form a factor F divided by EI. So we went over all of this. Basically, here your load is changing and your moment of inertia is changing. Your modulus of elasticity, it is constant. Okay, and that's of concrete what you use. Now what do you in the moment of inertia is not a constant, because as we said, your beam has a number of hairline cracks all along the length. So what you actually take should be a kind of average of because part of along the length of the beam, part of the tension face is uncracked and parts of it are cracked. So it should be some kind of averaging between the two. So how do we do this averaging? We said it is as per the code, and we looked at chapter 24. So that's it depends on what is your applied moment. So if your applied moment is less than 2/3 of the cracking moment, you just take the IG. So like I was mentioning in the review, the uncracked transformed it can be approximated as gross moment of inertia. You can ignore the small part of the converted tension steel. And when your applied moment is above 2/3 of the cracking moment, then that is your kind of interpolation between I gross and I cracked. Okay. Now coming to the loading history. So this was the most crucial point, what I went over in quite a bit of detail in the review, but here we will try to quickly look at it. So basically we are looking at deflections under gravity load. So you have dead load and live load. And don't forget the important point that deflections are always calculated for service loads, okay, not for factored loads, okay. So the main point is this: you need to check what is going on with that particular structure. In the most typical case, like we discussed, your structure is built, so it already has your dead load from everything, the self-weight, the plumbing and curtain walls and facade and everything. Okay, it already has the self-weight, and before the structure is being occupied by whatever machinery, people, anything, it has already undergone the elastic deflection due to dead load. Okay, now when something comes in, whatever further deflection takes place is after the elastic deflection due to the dead load. Okay, so uh, basically you have for delta, you have delta dead load instantaneous, elastic deflection due to dead load. Then you have delta dead load long term. So that's creep due to dead load. Now your live load, some part of the live load can cause long term deformation. So you need to you need to divide the live load into two parts. One is sustained part of the live load, other is unsustained part of the live load. Unsustained is just brief, like vehicles or people, so it's just there for a very short period of time. Now sustained is something like you bring in some big piece of machinery, it's going to sit for good, so, or for a long time. So that will be considered as a sustained live load. Even though it is not a dead load, it's still going to be acting for a while. So for sustained live load, you will calculate instantaneous deflection as well as long-term deflection. Now, what is the deflection that you need to consider, especially for anything that is considering the effect of any live load, which of course is coming in after the structure is already built. That is everything over and above the elastic deformation due to dead load. Okay, so how do you calculate that? That will include long-term deformation due to dead load, or long-term deflections due to dead load, or creep. And this is the long-term deflections due to sustained part of the live load. And these are instantaneous deflections due to sustained part of live load and due to unsustained. So total instantaneous deflection due to dead load. Now, how do you calculate this? So here, you need to do it in a particular way. For that, we looked at this moment versus deflection curve. So as you can see, the nature of this curve depends on the moment of inertia. It depends on how much is cracked. So if your moments, let's say your service load moment is always below the cracking moment, you will keep moving back and forth only along this line. Okay, your moment of inertia is not changing at all. You will always be using IG. So now let's say, but that is almost always not the case. Let's say that the green one that you see here, that is the dead load, and the yellow point is dead plus live. So you cannot just calculate deflection for live load separately. It will not give us the right answer. Okay, what we need is, after the dead load is already acting and you have the elastic deformation due to dead load, now when you bring in live load and it has further deflection, what's the difference? What's the additional deflection due to the live load? That's what we are looking for in the most typical scenario. Now, so D, you have delta DI. So in this graph, everything is instantaneous deflection, right? So first you have delta DI, what I'm underlining here. And that happens at this point. So your structure has reached this point by then. So of course, this is not the cracked moment of inertia, or this is not the gross moment of inertia. This is somewhere between cracked and gross. Now, now you'll put the live load, you further add the live load, now it goes to this point, right? So there is dead plus live load. And at that point, this is your deflection due to instantaneous deflection due to dead plus live load. Now, the difference between the two is going to give you your live load deflection, right? So you can see that your load path is not linear. So you cannot just do it separately for live load, separately for dead load and add them or something like that, right? Okay. Now there is a other case where let's say that at some point of time during the construction of the structure. Now this is also quite common for many structures. Where especially where you are bringing in very heavy construction equipment, let's say precast bridges, reinforced concrete pipes, box culverts, and so on. So that whatever loads were coming during the construction, they are much more than your live loads. Okay, so your construction loading is the most critical. That means before your live load is being applied, at some point it has already reached a very high level of cracking. Let's say this purple point. Now, since it already got there, from now on it will only go back and forth along this green line. Okay, it's going to be linear because okay, now what is your dead load? What's the point? What point corresponds to your dead load? Let's say here. So this. This is your dead load. Now, will you use the orange curve? No, you're going to use this green straight line because it already saw the loads which are much higher than what is coming in after that. So it has cracked to as much as it would. It's not going to get there anymore from now. So this point is your instantaneous deflection due to dead load. Now you go beyond that. Then it's again going along this line, straight green line to somewhere, let's say this point. So that's your instantaneous deflection due to dead plus live. Now the difference between them, that is your deflection due to instantaneous deflection due to live load. Okay, now there is some further points about the long-term deflection. Maybe I didn't mention during the review on Sunday. So very briefly, here is your typical beam section. There is your tension steel. Now what's going to happen? Your strain distribution will be, as usual, plane sections remain plane and so on. Let's say your neutral axis is here. Something like that, right? Now, as with time, your concrete will start creeping under compression, but still at those temperatures, unless you have some very high temperatures, the creep is negligible. So basically only concrete is creeping. And let's say after a certain period of time, that's your strain for concrete. But your steel strain is not changing, right? So your new strain diagram after maybe certain number of months will be like that. So that means with time, your neutral axis keeps moving down. So you can see that this is a quite complex problem. If your neutral axis keeps changing, then how do you calculate I? So if we want to do an accurate calculation for long-term deflection, this is going to be quite challenging. So what we do is we just use the code specification. Okay, so this is your lambda delta factor. So what you do is you just multiply this factor with your instantaneous deflection. Let's say that you want to get the long-term deflection due to dead load. So you just multiply delta di with the lambda factor, okay? Now lambda factor has two variables there. One is psi and one is rho prime. Of course, as you remember from your undergraduate, rho prime is the reinforcement ratio for compression steel. And what is psi? Psi you will look up from this graph. Psi depends on how much time has passed, okay? You will check how many months have passed after the structure was constructed or after, yeah, for basically from the point where it was loaded to where at the time period that you are checking. So you can just look up from here, that is psi. and then the rho prime, you have in the denominator the reinforcement ratio for compression steel. So why do we have that? We just mentioned that your compression, your steel doesn't really creep significantly. Now, so if you do have compression steel, that's going to restrict your concrete and compression from creeping, right? Because it itself doesn't creep. So it's only the concrete. So now your creep is reduced, and that's what is reflected in your code formula. So 1/50 times reinforcement ratio of compression steel. Okay, so we have kind of got over that. Now, I think we said that, okay, these methods, you have all covered in structural analysis. It's just for you need to be able to calculate the deflections for any general loading case. Now, for standard cases and standard boundary conditions, you can use your table. You can use this kind of a table. You have simply supported, you have propped cantilever, fixed, and all kinds of cases, and you have your deflections given there. But a lot of times, you know that on beams, you don't have a clear concentrated load at mid-span, distributed load, or anything like that. You may have various combinations. So in that case, you will have to get the formula yourself. So we went over one of the most useful is the moment distribution method. Okay, so I think this is where we kind of stopped, and now let's continue from there. This is where we stopped the review. Okay, so here you see that, okay, now one point to mention is that even though we are, for the class, we will be following mostly the ACI 318 2019 code, the 2014 code is still very much followed in, it's adopted, it's still being used in the industry. So if you look at the 2014 code or the older codes, the calculation of effective moments of inertia will be slightly different. So here you can see that that's the way your effective moment of inertia is calculated. And in the 2014 code, the interpolation was done differently. Let's go to serviceability chapter here. So that's your, for non-pre-stress members, that's your interpolation for the effective moment of inertia. Remember, we are interpolating between completely uncracked and completely cracked. It's somewhere in between. Okay. So, but they found, you know, in the code, it's always important to read the clause. So you can read here, before 2019, ACI 318 used a different equation, but that was shown to underestimate deflections for members with low reinforcement ratios and doesn't consider the effects of restraint. Okay, so if you have larger reinforcement ratios, you will not get much difference in your answer. But for low reinforcement ratios, this formula is underestimating your deflection. So that's why they gave an improved formula. Okay, let's get back. So I think we have compared. So your minimum depth is also a bit more stringent in your 2019 code. Okay, let's just have a look at that quickly. So if you go to chapter 9, for example, for beams, okay, so this is your minimum depth for non-pre-stressed beams, simply supported L by 16. I think this is more or less same, but let's just, they might have become more stringent. No, this one has not changed. Okay. L over 16, 1 and continuous, L over 18.5, 21 and 8. So this one has not changed. Okay. Now coming to continuous spans. Okay. So what is happening in continuous spans? So as you know, here you don't have uh, you have some positive moment region, you have some negative moment region. So let's say if you consider the positive moment region, what's going to happen? So your section will have reinforcing steel at the bottom, right? That's for the positive moment region. So if you look at your beam in the, remember from your undergrad, how do you put your steel? So this is your tension steel at the bottom. So you can either bend it and take it there to get your tension steel, or um, you could just stretch this all the way and then give your development length into, this will generally go into the column. So give your development length here, here. This can go through if it is continuous. For your tension steel, you will stop it at where the moment you get either your cutoff point or wherever you have sufficient development length, right? So you don't, your section looks different for um, your positive moment region and your negative moment region. So in your negative moment region, this is your positive moment region. Your rebars are at the bottom. In your negative moment region, your rebars are at the top. So you basically both sections are different and they will have different moments of inertia. So there is a one point that, okay, let's, okay, we will come to that in a moment. But how do you calculate effective moment of inertia um, for your continuous beams? So usually there are three formulae provided or suggested. So if you use some of these in your textbook, so let me just show you briefly. They are basically interpolating between. So you have your uh, you have your uh, you have your negative moment region and your positive moment region, and again a negative moment region. So in each of these negative moment regions, you will have a IE1 and IE2, and this is your midspan, the positive moment region. So you can use this formula when both sides are continuous. Okay, you can go with this. When only one side is continuous, like this side is simply supported, this is continuous, then you have IE1 in this region, and in this region you have IEM. So you go with this formula. And this is an alternative to the first formula, where, let me see, there is some particular instance where the 0.7 is more accurate. I'll just tell you that. Yeah, actually either one is fine. Maybe this could be somewhat improved result, but this is okay as well. Okay. So both of these are for both ends continuous. You will use either of these two equations. One end continuous, you use this equation. Okay. That's how you get it for continuous spans. Okay, long-term load. So we have just discussed how the neutral axis keeps moving downward. So it's actually not as if we want to uh, get a proper theoretical solution, it's actually very complicated. So moreover, accounting for the um, compression state. So what we do is anytime we want the long-term deflection, we just use this lambda delta factor. Okay, we multiply our instantaneous deflection with a lambda delta factor. So we just saw how to determine that from the code. Yes, so effect of loading history, this is the main thing we have discussed. Okay, so now let's just do one particular problem. Uh, okay, so here is our continuous span, all right? And we want to determine your, just a second. Okay, next we are coming to moment curvature. Okay, we will do a few of these and then we will start on moment curvature. Okay, let me have the moment curvature open. Just a second. Okay, give me 1 second. Let me stop the screen share for a moment. I will pull up the moment curvature example. Oh, okay, so now we are back. Uh, okay, so let's do this problem. So you have a beam which is part of a continuous span. Uh, okay, uh, yeah, let's go with this, which is part of a continuous span, and you want to determine your deflections at service load. Okay, what is the deflection at service load? Now, for this beam, the uh, now let's read it carefully because we need to know the loading history in order to understand what procedure to use to calculate the um, deflections. Okay, so Now, so we have, okay, there is a beam. It is part of the floor system of an apartment house designed to carry a dead load of this and service live load of this. Out of the total live load, 20% is sustained, 80% is intermittent. So it's just brief. So under full dead load and live load, so full dead load plus live load, this is the moment diagram given to us. All right. Um, Now the beam will have non-structural partitions and that will be damaged if large deflections were to occur. Okay, so these are partitions which are installed shortly after shoring is removed. So your construction after it is ready to start carrying loads, you take off the shoring, and shortly after then your these partition walls come in. Okay, so your what part of the total deflection is going to affect this um, shoring. Okay, so what we are going to do in this problem is there is an assumption that um, your structure has already been cracked to certain extent. Okay, so there was during construction there was some load which was quite high as compared to whatever live loads will be coming. So we will assume a linear path. All right. So remember we said that just to recall, that's the important point here. So let's go back here. If let's say if it is your regular kind of construction where you didn't really have very high loads coming in during construction, then this is WD as I showed here. Then when you add your live load, it goes to WD plus L. So the difference between these two is your uh, deflection due to dead load. Okay. Now, what we said that if it has seen some load which is heavier than that, okay, then it's going maybe along the straight line, this straight line, all right, this particular straight line all the time. Then your WD deflection will be actually at this point, and from beyond that it will go from 3 to 2. So that's your deflection due to dead load. So here everything is linear, just along this particular line. Okay. Okay. So that's the assumption we will be making for this problem. All right. Now, material strengths are as usual given Fc prime and Fy. So what is the deflection that what is the moment of inertia that we are going to use? Okay, so this is your you have some negative moment region, you have some positive moment region. So in your negative moment region, your flange is going to be in tension or compression.
Compression.
In your negative moment region, your flange will be under tension, right?
Okay.
Because okay, so let's draw the deflected shape of this beam. By the way, I really thank you, Samal, because all of everybody was just very silent, and I didn't know what was going on. So thanks to Samal. As you all already know, probably from your undergrad, you're visualizing the deflected shape of the structure is a very important uh, it's very important to do that. So how will the deflected shape of this beam look? So your something like that, right? So if you look at, so what's your positive moment region? Somewhere from here to here, right? So in this region, it is bending, it is sagging. The beam is sagging, right? Let's take a piece of paper. In that region, in between the two blue, or in this blue region, this is the positive moment region, right? So beam is sagging here. Now, for a second, let me stop the share screen. You see my camera like this, right? So when the beam is bending like this, you have tension at the bottom, right? So, and for the other two ends of the beam, your bending is hogging. So you will have tension at the top. Okay, hope it's clear now. So for the, like we said, the code allows us to use I gross for as an approximation of I uncracked transform. Okay, so uh, so in the positive moment region, your flange is under compression. So for positive moment region, you will use your section as that. That's your section for the positive moment region, okay? For uncracked properties. Now, for negative moment region, this flange is under tension. Even though there is no cracking started as yet, you must only use, it is an accepted practice and better practice to only use this part of it, okay? You don't consider the overhangs when the flange is in tension, even for uncracked transform, okay? Okay, so let's first calculate the moments of inertia. So what did we say? What do we need for deflection calculations? We need your moments and moments of inertia. So now we calculate Ig for, let's do positive moment region first. So what is your positive moment region? 14 by 24.5. So what is Ig? Can somebody quickly calculate and tell me? What is it? It is BH cubed by 12, right? So this is the first step for deflections, that you get your effective moments of inertia. So you need basically your effective moment of inertia, the EI, F over EI, then the F factor and your elastic modulus. So let's calculate all of the effective moments of inertia first. Okay. So what is this? This value is 14 times 24.5 BH cube by 12. So how much is that? Uh, so what is your eye cracked? So your, oh, I'm sorry. This is positive moment region. You do need the flange. So it's not just that. That will be for the negative moment region. You will need the flange. Okay. This is 75 inches. And your centroid for this is at 7.66 below the top. So can you all calculate I quickly? So you can divide it as into two parts any way you like. Maybe we can just do it as this thing plus the both these flanges together. So your I from the rectangular block is going to be your BH cube by 12 plus your A times D square, right? This is area times what's the distance? Your centroid for the rectangle is exactly in between 12.25. So your separation is 12.25 minus 7.66, that is 4.59 AD square. This is your moment of inertia contribution from the rectangular block. Plus from the flanges, what do you have? Your width is effectively 75 minus 14. So that is 61. So you have 61 times your depth is 5 inches. BH cube by 12 plus your area is 61 times 5 times 7.66 minus 2.5. How much is that? 5.16. So let's do all of that. Your first part is 24383.5 plus second part is 858756.23. So that comes to 33139 point. Can somebody verify it for me? Let me see. I have gone over this. Sure. Yeah, I think we are good there. Okay. So what's your cracked moment of inertia for positive region? So your cracked section for the positive region is going to be like this, right? So this is in compression, and um, then you have your tension steel. So I hope you didn't forget how to calculate the positions of neutral axis and so on for a cracked section. So let's just take a picture of that. Okay. So what's your uh, crack moment of inertia here? You first need to determine where is the neutral axis. So let's take so we have assumed that the centroidal axis is within the flange, and I think that is turning out to be right. So anyway, let's calculate. We don't know where it is beforehand. Let's assume first inside the flange. So that is your KD. Okay. Now, uh, now this is your BF. So you have BF times KD. That's your area, times what's your distance from the neutral axis? It's KD over 2, right? So this is equal to your tension steel, transformed tension steel, times D minus KD over 2. I'm sorry, D minus KD, right? Uh, I mean, anyone who is, you are listening and you have any question, please feel free to ask, okay? So, not sure who all had to leave, but okay. Let's calculate this now. You can cancel out 1D. These all you all know how to do. So N times S is given to us 28.64. We have in the tension steel 2 number 9 and 2 number 8. So you can verify this number just so that you're not rusty on all this rebar and everything. Let's see, I should have the rebar chart here. No, okay, I can pull it up from. Have here the rebar. 2 number 8, 2 number 9. What's the total area? 2 times 0.79 plus 2. 2 times 0.79 plus 2. So that's 3.58. And you multiply by your modular ratio 8, you got 28.64, right? Okay, so that works out.
Dr. Nathan, can you email us that table?
Yes, sure.
Thank you.
Let me do that right away. Okay, let's. I will send it. It's coming. Okay. Now, BF is 75 times K square times D. D is 22 over 2. This is 28.64 times 1 minus K. Okay. So you have your quadratic here. So if you simplify things, you can get K square equal to, so 28 3, 4, 7. So you get K is 0.17. 0.17. This is K. So your
what is K, Dr.
you remember for cracked section, it is everything is still linear elastic, right? Concrete is still, we are assuming that concrete is still in below around 0.7 FC prime, and for service loads, and your steel is also below Fy, right? Fs is below Fy and your Fc is below 0.7 Fc prime. So your stress distribution is going to be how? It is still like the elastic beam analysis. So this is just your transformed section. Kd is just the depth of the neutral axis from the top of the beam. Is it clear? Hope so.
Yeah, thank you.
Okay. So what is Kd now? So this implies Kd is you multiply 0.7 times 22, 3.73, less than 5 inches implies that within flange. Our assumption is correct. Okay, neutral axis is within the flange. Okay. Now that we got our neutral axis, what is our moment of inertia? So that's our $75 inches 3 by 3. Then you have your tension steel, 28.64 square inch. You have your D value, 22 inches. And oh, this is not 3. This is 3.73. Okay, so now can we quickly calculate I? So this is the place where is your neutral axis. So for your 75, it's going to be basically 75 times BH cube over 3. And for this one, it's going to be 28.64 times 22 minus 3.73 over 2, the whole square, right? So what's all that? One two nine zero 8. Okay, so now we have for our positive moment region, this is our cracked moment of inertia, and this is our gross moment of inertia. So what is our effective moment of inertia? So IE, we will go as per the code, 2019, okay? But like I said, still many companies might be following the 2014, especially a lot of times the analysis and design are done using software. And I think software must have already updated, but it could be, okay? Okay, so we don't know the cracking moment as yet. Let's determine the cracking moment. Okay, just a second. Okay, so how will we determine our cracking moment? What is FT? Does any of you remember directly? The modulus of rupture, 7.5 square root of FC prime, right? You don't, then sometimes I'm just assuming that you have all taken it in the undergraduate course, but for any of you, okay, here is the just a second. Should be here, FT. There's some question in the, okay, oh, okay, so, okay, so now I have one more question. I have a request. If I know I will send to whole class, but any of you who have not taken undergraduate reinforced concrete design, can you not, don't put right now in the, can you please send an email to me? Anybody who has not taken undergraduate reinforced concrete design, please send me an email. Okay, so I will share the notes of the undergraduate course with all of you. I mean, with those of you who need it. Okay. Uh, okay, it is 7.5 square root of. Okay, let me just get it to you. Okay. Uh, it should be in the same chapter as. Okay, so okay, there you go. Modulus of rupture. Okay, I forgot the clause number, but now I see it. Modulus of rupture is 7.5 lambda square root of Fc prime, as you see here, right? Okay. Oh, sorry, it is Fr. 7.5 square root of Fc. So what is our Fc prime? 4000, right? 4000 psi. How much is that? 474.34 psi. Okay, so you see this in the here is your Ig. So this is the stress that you see in the bottommost tension fiber. You know your Ig is so much. So your 474.34 is your cracking moment times what's the distance here of the neutral axis? 24.5 minus 7.66. 16.84. So times 16.84 divided by here. This is inches, this is psi, and I is 33,139.72. So you get your MCR is 77.79 kip foot. This is MCR. Okay. Okay. Now, okay, we have got IG and ICR. Okay. So what is the interpolation formula? Let's get it now. Or one request I have, those of you actually the undergraduate reinforced concrete material, it might be difficult to email everything. So anybody who didn't take the undergraduate reinforced concrete design course, if you can just come to my office, like whenever it works out. If you can bring your USB, I will copy everything there. Okay. Okay. So let's come back here. So in the very beginning, we are interested in okay. So we make the assumption that at some point of time before the live loads actually come in, it has seen the full load. The structure has seen the full load during construction. So that's your moment diagram. Okay, it has seen that. This is what we will use to calculate our effective moment of inertia. So let's go use you need your MCR and your MA. So MA, that MCR we just got 77.78 kip foot, and your MA M applied, we take it as in the positive moment region 162 kip foot. Okay. So what's your I? So your MA is obviously greater than 2/3 of MCR. So which means your I is I effective. So for positive moment region is ICR, use the 1 minus 2/3 MCR by MA whole square 1 minus ICR by IG. So what's our ICR? 12,908.55. 1 minus 2/3 of 77.78 divided by 162 square. 1 minus ICR divided by IG 33139.72. So let's calculate all of that. So this is 12908.55 divided by 1 minus 0.1025 times 0.61. So this is 13770.2. So this is your effective moment of inertia for IE for positive moment region. Okay. Now, how about the IE for the negative moment region? So your negative moment region, let's do that now. So like we said, negative moment region, we are going to ignore the flange since the flange is under tension. So we will only take this rectangular block. So your IG is BH cubed by 12, which is 1715.15. Okay, what's your ICR? Okay, so what is your cracked section? I think it's given to us. Let's use it. So here is your cracked section for your just one moment. Uh, so you have compression steel as well here. Um, that is the 11.06, and you have your tension steel as well. Now, now we first need to calculate KD here. So let's assume some value of, excuse me, so we don't know how much is KD. Okay, now your NAS times D minus KD must be equal to this is B times KD times KD by 2 plus the N minus 1 AS prime times KD minus 2.5. Okay. So let's quickly solve this. 44.48 times 22 minus, let's just take KD as X. B is 14, X squared by 2. N minus 1 is, okay, all this is 11.06 times, okay. So let's quickly solve this. Okay. So 8.66. So KD is 8.66 inches. So let's calculate our I cracked. So you have your 44.48 times D minus KD square plus you have your 14 times 8.66 cube by 3 plus you have your 11.06 times 8.66 minus 2.5 square. Okay, so what's all that? Let me check. Okay, 11,365.97. Okay, so that's your crack moment of inertia. So what's your effective moment of inertia for this negative moment region? So we need the first we need cracking moment. So MCR is FR times I gross divided by Y. So FR is 474.34. I gross is 17157.15. This is PSI divided by Y. Y is just 12.25. So what do you have? $55.36 kip foot. Okay, so let's use our interpolation once more. So in the negative moment region, again, we are assuming that the full load has already acted before the construction is completed, okay? So 225 foot kips. So we have M applied is 225 foot kip. So we will be using this formula. So your I effective is ICR 1 minus 2/3 MCR divided by MA square 1 minus ICR over IG. So let's plug in all of that. ICR is 11,365.97. One minus 2/3 of 55.36. MA is 225. 1 minus ICR is 11,365. Over IG is 1717157. Okay, so all that works out to 11365.97 by 1 minus 0.027 times 0.3375. So 11470.5. Okay, so we have your I effective for the negative moment region as well. So what did we say? Now we need to use the formula. We will use I effective is 0.5 IE midspan, 0.25 from each of the two negative moment regions, right? Basically, it's an average. So since both are same, it's an average. So you have 1/2 of, so your midspan positive moment region is 13770.2 plus 11470.5. Okay. So this is our first step. We have arrived at effective moment of inertia. Remember, what is the deflection? It's F over EI. So now we have to determine what is F. Okay. So what's F? Let's look at our moment diagram. Okay. Okay, this is your moment diagram, right? From here, what is your deflection? So your moment by EI is the curvature diagram. So the easiest way, like when you already know the moment distribution diagram, a bending moment diagram, then your easiest way to calculate deflection is by using moment area method, the theorem 2. So, so just it is like it's like a ghost class. Everyone is so silent. So, um, do you did any of you get a chance when in the last lecture, the Sunday's recording, I was going over the moment area method. So, did anyone get a chance to listen to that part? If not, I can just go over it again.
I did actually.
I couldn't hear.
I looked at the first lecture. Yeah, I did.
Okay, you did. Okay. I hope most of you looked at it. So if you use the moment area method number 2, then what you do is you can use to get this maximum deflection, which is going to be at mid-span. You can take the tangent at this point and get the distance from this endpoint, which is fixed, right? So basically, you're using the TAB method. So this is A and this is B. So your deflection will be given by TAB. So your TAB is going to be moment of this moment diagram about B, right? Moment of this moment diagram as measured from B. So, the easy way is to write this moment diagram as a superposition of two parts. One is this. This is positive part plus this is negative. So in the positive one, this peak is 387 foot kips. And in the negative, we have 225. So if you add these two, you will get this moment diagram. So for this, taking the moment of uh, all this area from A to B, about B, that's a bit more complicated. But if you can do this, this is very easy. Take the moment of the parabola. Since moment is directly proportional, you can superpose moment of this parabola and moment of half of this rectangle. Okay. So moment of the parabola is how much? 2/3 area is what? 2/3 base. Base is 12.5 feet times height is 387 foot kips. Everything by EI. So 1 over EI times this is the area, 2/3 of base times height times what's the centroid distance of the parabola from the end B? Okay, anybody remembers? It's either 5/8 or 3/8. Let me open that up. Okay, so for a parabola, so distance from this side is 5/8. Okay, distance from, as you can see here, distance from the left end is 3/8, and distance from the right is 5/8. Okay, let's do that. So 5/8. Oh, I should have guessed that because it's closer to this end. That was a bad. Okay, 5/8 of 12.5 feet. Okay, so this is in the unit of numerator. You have unit of cube foot square. Now, plus or minus 1/EI. This area is simple. 225 times 12.5. That's the area. Centroidal distance is 12.5/2. That's 6.25 foot square, cube foot square. So all that is 1/EI 25,195.31 minus 17578.125. All that comes out to 7617.185. Cube foot square over EI. Okay, so this is our general formula. This is for the full D plus L, okay, service load. Now, as we said in this problem, we are assuming the linear load path that we are assuming that it goes from 0 to 4 back and forth along the line 0, 4. So we don't need to worry about changing moments of inertia. So it's all the same I effective. So I effective, we will use what we calculated earlier, that is this value. Okay. So so what is E? E is 57,000 square root of FC prime That's your elastic modulus, if you remember from the code. (3605) KSI. Okay, so first we will calculate delta D plus L instantaneous. This is how much? Oh, hello. Oh, just a second.
Yes, I think my girl is student
Yeah.
who is taking your class, I think.
Yeah.
So you change it to the morning.
Yeah, but I can change it again.
No, that's fine. That's fine. So I just wanted to make sure because so start at what 7 to what time?
9:30, 10.
9:30. Okay. Which days?
Only Wednesday.
Only Wednesday.
Yeah.
Okay, that's fine.
Should I change it back?
No, that's fine. That's fine.
Sorry, where? So just for the instantaneous deflection, we will do it like 7617.185. So you multiply 144 to convert this to kip inch square divided by, you have your 3605 KSI, and then you use our effective moment of inertia 12620.35. So as you can see, now you will get what will your answer come out? So this is KSI, kips per square inch. So you take kips out. Your numerator has kip inch square. Let's see. So we should be left with an inch. So you have kip inch square divided by kips per inch square times inch. Oh, it shouldn't all be cancelling exactly. Okay, let's see. Okay. So you have, this is foot cube, sorry, in the numerator. So you have area and times moment. So there is another 12 here. So let's fix this. 12 cube inch cube. Okay, so your final answer will come out in inches. So let's just calculate that. 7617.185 times 12 cube divided by 3605 times 12620.35. So that is 0.289 inches. Okay, this is when we put the symbol, this is I is instantaneous deflection due to dead plus live load. Now we said everything is along a straight line, right? So if you want instantaneous deflection due to just dead load, how do we do it? We just scale it. So instantaneous deflection due to just the dead load. So well, let's go back to our question. Oops. Okay, just the dead load is 1.65. Total service live load is 3.3. Let's come back now. So WD is 1.65 and WL is 3.3. Okay, let's forgot the value. Yes, okay. So since everything is linearly proportional, we can just scale it up. Okay, so this is for total dead plus live. So only for dead, we would get 1.65 over the total 1.65 plus 3.3. Remember, this is only because of the assumption we made that everything has been cracked to the max beforehand. We are able to do this. Okay, if it's not moving along the straight line, we cannot do this kind of proportional analysis. Zero 0.0963. So delta L I is delta D plus L I minus delta D I. So that is 0.192 inches. So what's important for us? Let's read the question, come back to the question. So that part of the total deflection that would adversely affect the partitions. That means everything has been built up already. That means delta dead load instantaneous is already there, and then the partitions are put. So what will matter now is delta instantaneous due to live load and delta long term due to dead load, delta long term due to sustained part of live load. Let's calculate those. Now how to calculate the uh, the delta long-term portion due to live load. Let delta DL. So we said this will be the factor lambda delta times delta D I, right? So now we need to look up lambda delta. So this is after how many years? So it is just not mentioned. When nothing is mentioned, that means you just assume a really long time, and we will use a value. So this is after very long, it's 2. 2 is the asymptote value. So just let's use 2. So delta, this is 2 times of delta DI was 0.0963. So that is 0.193 inches. Now you also have delta sustained part of live load long term. So what is the sustained part of live load? So let's do 80% of the total live load. So total live load causes 0.192 inch instantaneous. So sustained part of live load, let's do instantaneous first, will be just 80% of the delta Li, which is 80% of 0.192. 0.154. Okay. Okay. So now we have delta D long term, delta SL initial. Okay. So this is delta SL long term will be 2 times of this. 0.307. Okay, so what's the everything except delta dead load initial? That's what will count for the partitions because they came in after the construction happened. So your delta dead load long term, delta sustained part of live load long term, plus delta live load initial. All this will matter. So that is 0.193, then 0.307, then your live load instantaneous is 0.192. So 307, 193, 192, 0.692. Okay, so this is the value. The person who is installing the partition walls will say that, hey, I cannot have more than certain deflection here. If not, my partitions are going to get damaged or something. Then we already calculated everything. We will tell him, hey, you're going to get around. So remember, deflections are always approximate, okay? So if you got this value, you will tell him, hey, we are looking at around 1 inch. So you just need to be in the ballpark. Like if you say roughly 1 inch, that's enough. So you cannot say, oh, between 1 inch to 8 inches. That's meaningless, right? That's not what we just want in the ballpark, but we cannot say, oh, is it 0.692? No, or is it 0.713? No, we cannot say that accurately, but we want in the ballpark. Okay. So this is the number. The guy who is installing the partitions, he will want to know. He will or before we even install anything, even construct anything in the design phase, we will know that, hey, partition walls are going to be coming and they cannot sustain a deflection more than, let's say, 2 inches. Then you will say, okay, we are good. Okay. Okay, so I think that's all for today. I hope you all got everything. Excuse me. I hope you all got everything. If not, I'm here in the office and most of the time I'm here till around some days up to 7:30, some days up to around 4:10. So you can ask me. 2 points, like if anybody is there who did not take the undergraduate reinforced concrete design, or it's a long time since you took that, I have notes for most of those. I can, if you bring your USB, I can just copy it into there. And one more point is that we will be having one guest lecture. Now, this is by a speaker coming from American Concrete Pipe Association. Now, we have to kind of adjust to his time a bit. So I gave him, excuse me. So I gave him the Wednesday morning time, and I also asked him Thursday evening time. So, and the thing is, he will come in person. He didn't give me the date as yet, but most likely he may come sometime in October. But he will be coming in person, and like this is someone with almost more than 40 years experience in reinforced concrete pipe and box culvert design. So please don't miss his class. I will know maybe in the next week. I should know exactly when he is coming, and I will give you that time. If at all it clashes with anything, please, you can make arrangements so that you can come in person, okay? I think only one guest lecture for our semester. If there is one more, I will let you all know, okay?
Okay, thank you.
Thank you, Dr. Nasim. So we're meeting again next week at the same time. Yes, 7.
Wednesday morning. Yes, yes.
Okay.
Okay. Okay. One request to everyone. So now that we covered a fair bit on deflections, I'm going to post. I mean, we did it for continuous beam or continuous one-way slab. So if it's just the regular simply supported prop cantilever, all that you can do on your own, right? So I will post 1 or 2 homework problems and you can work on that. Okay.
Yeah, thank you.
Okay. Thank you.
Yeah, thank you. Bye-bye.
Thank you, Dr.
Thank you.
When is it due?
Yes, usually 1 week you can take. But if you need more time, just tell me, because many of the assignments in this course, we may not have many problems, but they tend to be a bit long, especially when we come to continuous beams design, momentary distribution, all that. We will start having a software part as well. We will be using either the SP beam, SP slab, or, but I mean, in short, it's going to be a bit long. So by the end of 1 week, if you have not got your solution, please let me know and you can take a few days more. Okay.
Okay, thank you.
Okay. Thank you. Okay. I'll stop now.
چه موقعیتی رو داد امیر حسین فرهادی
Oh, okay. That's not.